record. Nope, can't do that. Okay. Close that down, open that up. Okay. So so here we're dealing with something called conservative and non-conservative forces. So, oh, I thought I was sharing my screen. Here we go. Perfect. And actually, let me pull up the answer keys. That might be a little better, because sometimes I don't know the exact words they want here. And then we'll do one of the problems from scratch. Here we go. Yeah, so often both conservative and non-conservative forces act on an object at once. So non-conservative forces will be like friction or air resistance. Conservative would be, we consider like kinetic or potential. The total energy is constant. That is always true. It may change to be transformed one to another, but the total remains the same. Efficiency we'll talk about at a later time, so let's not really concern ourselves with that. But let's actually now go to the blank version and clear. So again, often both conservative and non-conservative forces act on an object at once. Total energy is constant in a process. It may be transferred from one system to another, or it may transform, but the total energy remains the same. And again, we'll worry about efficiency at another time. So let's look at the first one here, and then I'll have you guys then do a little practice. Okay, so rocket starts on the ground at rest. Its final speed is 500 meters per second, height is 5,000 meters. If the mass of the rocket stays approximately 200 kilograms, find the work done by the rocket engine. So that's kind of like the applied work, I guess you could say. Which is not conservative. So we're going to do this: KEI plus PEI plus our work that's not conservative equals KEF plus PEF. So you're starting at rest, so that's going to be 0. That's going to be MGH. We're going to work this out in just a bit. KF is going to be 1/2 mv squared. You have no potential energy at the oh, it's the other way around. Hold on a sec. Yikes. Yeah. Let me back up a little bit. It starts on the ground at rest. So it's actually 0 also. Yeah, that's because you're at rest. And that's because you're on the ground. Okay. Now, the kinetic energy is going to be 1/2 mv squared plus mgh. So we do know our mass, which is 200. It does reach final velocity of 500. again, 200 times 9.8 and times 5,000. And final answer will be in joules. So that's what you want to do for that one. And actually, let me pull up the answer key so just to save time so I don't have to actually punch this in the calculator. Yeah, you can see it's exactly what they're doing here. 0 for the height, 0 for the velocity, and you work all that out, and you should get 34,800,000, I think. So let me, yeah, if you work out correctly, you should get this. Or 3.48. So that one seems pretty straightforward there. Let's look at another one here. A 1,500 kilogram car brakes fail and it coasts down a hill from rest. The hill is 10 meters high and the car is at a speed of 12 meters at the bottom of the hill. So again, we're going to kind of do the same thing. Let's change colors here. KI plus PI plus work that's not conservative, which is going to be that right there, we equal KF plus VF. So right now you have no kinetic energy because you're at rest, but it's going to be 1,500 times 9.8 times the height, which is 10, plus your work that's not conservative, equals your KF, which now we know is going to be 1/2, your velocity squared, which is 12 squared, no potential energy. Work it all out. That's going to be 750 times 144. And at the same time, I'm going to move those stuff over to the side. That'll be 1,500 times 98. So let me get calculator here. 750 times 144 minus 1,500. So that's 108,000. 1,500 times 98. And that should be negative because it's work you're losing that energy. It's working against you. So we kind of say this is like energy released because it's negative. As heat due to friction. I mean, friction is really easy concept to understand when it comes to heat. Like if you rub your hands together and it gets hot, that's friction, right? Or if you actually wait until a train passes by, but if you see a train pass by and feel the rails, they're gonna get really hot as well. So that's what we anticipate for all that. Yeah, you get negative 39,000, just like we got there. Let's do one more of these, and then I'll let you guys do some practice. So any questions so far? Nope. Again, this is being recorded, so there's a recording here. All right. Captain Proton's rocket pack provides 800,000 joules of work to propel him from resting on a ship, which is near the Earth, to 50 meters above it. Okay. Captain Proton's mass is 90 kilograms. What is his final velocity? Okay. So same thing. I'm not going to stray from what we've been doing. KI plus PI plus your non-conservative work equals KF plus PF. Okay, so I'll have some other people help me out here. People haven't really called on today. So, so Kate, I haven't called on you yet. What do you think his initial kinetic energy is going to be if he's resting on his ship right now?
0.
Good. And he's on the ground. He's on the Earth. So what do you think the initial potential energy is also? Remember, he's starting on the ground.
Oh, 0.
0 again. Yep. And then what do you think the 800,000? Where am I going to put that?
For the W.
Yeah, because that's applied. Yes, this is an applied force. Yeah, anything that's applied or friction or air or whatever is going to be non-conservative. So good. Okay, and I'll finish off. Thank you, Kate. The final, we don't know. So 1/2 mv squared. And the potential energy is going to be mass times gravity times height. Well, obviously I have 800,000 equals 1/2. Your mass is 90. Velocity we do not know. That's what we want to find. The mass again is 90. The gravity is 9.8. And the height, of course, gets to 50. And you're just solving for V. That's all you're doing. So if you do your math correctly, that should be 45 V squared plus, let's see here, 90 times 9.8 times 50. Simple cell phone could do the trick here. 800,000, and kind of just work it out. $755,900 equals 45 V squared divided by 45. And then you got to square root all that junk. You should get about 129.61 meters per second. If you guys watch that SpaceX thing that happened, I think a couple weeks ago, it was a joint effort from NASA and full SpaceX. That rocket was going pretty darn fast. If you actually do a conversion, 129.61 meters per second converts to miles per hour. Yeah, nearly 300 miles per hour. So it was going really, really fast. Actually, I think it was going even much faster than that. But at 50 meters at least, which is probably what, 150. No, it's actually, it's not even that high. So it probably be accelerating even more afterwards. So cool. Okay, so now this is perfect for around 1 o'clock. So I'm gonna have you guys do some practice problems. Just take a quick look here, what would be good for us to do. Okay. So maybe we'll do like just the first 4 problems, and we'll do more of these probably tomorrow. So I'll have you guys do, if you guys get stuck, just call me over to your room. Yeah, I think we'll do those. And I wonder when they talk about efficiency, probably near the end. I don't know. Anyway, yeah. So 2, 3, 4, 5. So I'm gonna have you try those problems. 5 might be kind of a doozy. Let's see how that goes. I have faith in you guys. So 2, 3, 4, 5. Clear. Stop sharing.